Welcome to the deep dive. Today, we're going to be exploring something that sounds kind of complex.
Yeah,
But it's actually woven into, like, the fabric of our everyday lives.
it really is.
Entropy.
Yeah.
It's a concept that can help us understand everything from, like, why time moves forward to why your headphones always seem to get tangled. We've got some great source material on this classic thermodynamics, mind-blowing cosmology.
Yeah, some really interesting stuff.
Even some stuff about how entropy connects to information theory.
Absolutely.
Ready to get our minds stretched.
Absolutely. I'm excited for this one.
So when we talk about entropy,
Yeah.
what are we really talking about?
At its core, entropy is a measure of disorder or randomness within a system.
Okay.
You've probably heard the phrase, entropy is always increasing, and that's really what we're getting at here.
So it's more than just like a messy room?
Yeah.
Although it can definitely relate to that.
Absolutely. We've all been there.
But how do we actually measure this disorder?
Right.
Is there some kind of entropy meter?
Well, no literal meter,
Okay.
but we can quantify entropy thanks to the work of some brilliant minds.
Okay.
One of them was Rudolf Clausius, a German physicist.
Okay.
He was studying heat engines back in the 19th century.
Mm-hmm.
And he realized that heat always flows from hot objects to cold objects, never the other way around.
Right?
And to describe this tendency, he came up with the concept of entropy.
So entropy is like a measure of how much energy has spread out,
Yeah.
how evenly distributed it is.
Exactly. Think of like a drop of food coloring in a glass of water.
Okay, yeah.
Initially, it's concentrated in one spot, a state of low entropy.
Right.
But as it spreads out and mixes with the water,
Yeah.
the entropy increases.
Okay, so I'm picturing that
Yeah.
the color going from a tiny dot to like disperse throughout the entire glass.
Exactly.
So basically, the more spread out the energy, the higher the entropy.
Yeah.
But you mentioned quantifying entropy.
Yes.
How do we actually put a number on this?
Right. So that's where Ludwig Boltzmann comes in. He built upon Clausius's work
Okay.
and gave us a statistical interpretation of entropy.
Okay.
He realized that it's all about the number of possible arrangements within a system.
Okay.
The more possible arrangements, the higher the entropy.
So more arrangements equals more entropy.
Yeah.
Can you give me an example that isn't about food coloring?
Sure, imagine a brand new deck of cards,
Okay.
all neatly arranged by suit and number.
Yeah.
That's a state of low entropy.
Okay.
But when you shuffle the deck,
Yeah.
you increase the entropy because now there are countless ways those cards could be arranged.
So it's like with a new deck, there's really only one correct order.
Right.
But after you shuffle, any arrangement is basically as likely as any other.
Exactly.
So suddenly you've got billions of possibilities.
Precisely. And the universe, it turns out, loves possibilities.
Yeah.
It tends towards those states with the most possible arrangements,
Okay.
the ones with the highest entropy. And that's where the second law of thermodynamics comes into play.
Okay, so you mentioned that earlier.
Yeah.
This is where the entropy is always increasing rule comes in.
Exactly. The second law states that in an isolated system, a system where no energy or matter can enter or leave, the total entropy can only increase over time,
Oh.
or at the very least stay the same.
Okay.
It never decreases.
Okay, so no going back.
Right.
Once things get mixed up,
Yeah,
they're basically stuck that way.
pretty much.
No cosmic unshuffling the deck.
In an isolated system, no.
Okay.
It would be like trying to unstir your coffee after you've added cream.
Right.
It's not impossible, but the odds are so astronomically against it that we never see it happen naturally.
So this seemingly simple law,
Yeah.
entropy can't decrease, has some pretty big implications.
Huge implications.
Yeah.
It's not just about messy rooms or unshuffled decks of cards.
Right.
It dictates the flow of heat, explains why perpetual motion machines are impossible,
Okay.
and even gives us a clue as to why time moves in one direction.
Hold on. Time moves because of entropy.
There.
I'm going to need you to unpack that one because my mind is officially starting to bend.
Well, think about it. Why does time seem to have an arrow,
Okay.
always pointing from past to future?
Right.
Why can't we rewind events like a movie?
Yeah.
The second law, with its emphasis on increasing entropy, suggests that time's arrow is actually an arrow of increasing disorder.
Okay.
As the universe evolves, its total entropy increases. And it's this increase that gives time its direction.
Okay.
Yeah.
So the universe is basically on like a one-way trip to maximum entropy.
Yeah.
What happens then?
That gets into some fascinating and maybe a bit unsettling territory.
Okay.
There's this concept called heat death,
Okay.
which paints a picture of the universe reaching a state of maximum entropy.
Okay.
Everything would be spread out, evenly distributed, no temperature differences.
What?
basically a giant lukewarm soup of nothingness.
Whoa.
No stars, no planets, no life, just maximum entropy and no potential for further change.
Okay, definitely unsettling.
Yeah, it's a little bit bleak.
So no more exciting cosmic events, just a universe stuck in a state of ultimate boredom.
It seems that way.
Is there even like a limit to how much entropy the universe can have?
Those are questions that still have physicists scratching their heads.
Yeah.
Is there an absolute maximum entropy state?
Mm-hmm.
A point where the universe is as disordered as it can possibly be?
Right.
Or can entropy continue increasing indefinitely? We don't have all the answers yet.
Yeah.
Which I have to admit is part of what makes studying entropy so captivating.
I can definitely see how this gets interesting.
Yeah.
We've gone from messy rooms to the fate of the universe in just a few minutes.
That's entropy for you.
That's impressive.
Yeah.
But before we get too lost in like the cosmic implications,
Right.
let's bring things back down to Earth for a bit.
Okay.
You mentioned earlier that engineers have to think about entropy when designing things.
They do.
How does that work?
Well, the second law puts some hard limits on what we can build
Okay.
and how efficient our technology can be.
Right.
It's like a fundamental constraint on all our clever inventions. Any process that involves energy transformation will always result in some energy being lost as unusable heat,
Okay.
increasing the entropy of the surroundings.
So it's like a cosmic energy tax.
Exactly.
No matter how clever we are, we can't create a perfectly efficient system.
Exactly. We can, however, get pretty clever about minimizing that entropy tax.
Okay.
Take car engines, for example.
Okay.
One of the key goals in engine design is to reduce the amount of energy lost as heat
Okay.
to make them more efficient and reduce their environmental impact.
Right.
Same goes for power plants, refrigerators, pretty much anything that involves energy conversion.
Okay.
Understanding entropy helps us build better, more sustainable technology.
So we're using the laws of physics to create a better world.
Exactly.
That's pretty cool.
It is.
But I'm sensing there's even more to this entropy story.
Oh, there's plenty more.
What about other fields? Does it have any role to play in, say, the world of information?
It absolutely does. And this is where things get really fascinating.
Okay.
The concept of entropy is actually central to information theory,
Okay.
which deals with things like data transmission, compression, and encryption.
Wait a minute.
Yeah.
How can disorder and randomness be relevant to information?
Right.
Isn't information all about order and meaning?
It seems counterintuitive.
Yeah.
But think about it this way. The more random and unpredictable a message is, the more information it contains.
Can you give me an example?
Sure.
Okay.
A string of completely random characters has higher entropy than, say, a message that just repeats the same word over and over.
So more entropy in a message actually means more information.
Yes.
Okay.
It's one of those concepts that takes a little while to wrap your head around.
Yeah, this is blowing my mind a bit.
Yeah, but it has profound implications.
Okay.
For example, think about data compression.
Okay.
We compress files to make them smaller to reduce redundancy.
Right.
But at its core, compression is about finding patterns and order within the data.
Okay.
Which means reducing its entropy.
So a highly compressed file would have low entropy.
Yes.
Whereas a raw, uncompressed file would have higher entropy.
Exactly.
Okay.
And this same idea applies to encryption.
Okay.
Strong encryption relies on creating keys that are highly entropic,
Okay.
meaning they're as random and unpredictable as possible.
Mm-hmm.
This makes it much harder for someone to guess the key and decrypt the message.
Right.
So in a way, we're using entropy to fight against entropy.
Okay, that's both brilliant and incredibly complex.
It is.
I think I need a moment to process all of this.
Take your time.
Okay.
It's a lot to digest, but trust me, the implications of entropy are worth exploring.
Okay.
It even touches on something as fundamental as life itself.
Okay, now you've really got my attention.
Right.
What does entropy have to do with life?
Yeah.
Aren't living things all about order and complexity?
That's what makes life so fascinating from an entropy perspective.
Okay.
Living organisms seem to defy the second law. They create order and complexity out of simpler molecules, building intricate structures like cells and organs, and maintaining a high degree of internal organization.
So are we saying that life is like some kind of entropy rebel?
Yeah, in a way, yes.
Okay.
But it's a constant battle,
Okay.
and one that requires a lot of energy.
Okay, can you explain what you mean by that?
To maintain their internal order, living things constantly need to take in energy from their surroundings,
Okay.
whether it's from food or sunlight.
So plants absorbing sunlight, animals eating food,
Mm-hmm.
that's all about fighting against entropy.
In essence, yes.
So,
Life is this incredible balancing act between creating order within itself while contributing to the overall entropy increase of its environment.
right.
It's a delicate and ultimately temporary victory against the relentless march of disorder.
Whoa. Okay, you've just given me a whole new perspective on life, the universe, everything.
Glad to hear it.
My brain is officially full for the moment.
That's it. We'll take a break.
But I am definitely hooked on this whole entropy thing.
Excellent.
We've covered a lot of ground today, from the basic definition of entropy to its implications for the fate of the universe and everything in between.
It's quite a topic.
We'll need a moment to process all this amazing information.
For sure.
But don't worry, we'll be back soon to dive even deeper into the strange and wonderful world of entropy.
Absolutely.
Stay tuned.
Sounds good.
Welcome back to the deep dive. Before we went to commercial, we were talking about how life is this amazing balancing act, fighting entropy to stay organized,
It is, yeah.
but ultimately increasing the disorder of the universe around it.
You're right.
A pretty wild concept.
It really highlights how deeply intertwined life and entropy are.
Yeah.
Life is constantly taking in energy
Mm-hmm.
and using it to create order within itself,
Yeah.
whether it's building cells or maintaining a stable body temperature.
You're right.
But in doing so, it inevitably releases heat and byproducts into the environment,
Okay.
increasing entropy overall.
So it's like a constant uphill battle for life.
In a way, it is, yeah.
But speaking of battles, you
Mhm.
hinted earlier that entropy even plays a role in warfare,
It does.
specifically in the context of information and encryption.
Right.
How does that work?
Well, in the world of espionage and cyber warfare, information is a valuable weapon,
Okay.
and protecting that information is paramount.
Right?
This is where entropy comes in.
Okay.
As we discussed earlier, the more random and unpredictable a message is,
Yeah.
the higher its entropy.
Right.
And in the context of encryption, that's a good thing.
So you want your secret messages to be as high entropy as possible.
Exactly. Strong encryption relies on creating keys that are highly entropic,
Okay.
meaning they're incredibly difficult to guess or crack.
Right.
It's like trying to find a specific grain of sand on a beach.
So the more entropy in the encryption key,
Yeah,
the more secure the message is.
precisely.
That makes sense.
It's a constant arms race,
Right.
with code makers trying to create ever more entropic keys,
Yeah.
and code breakers trying to find ways to decipher them.
It sounds like something straight out of a spy movie.
It does. It does.
But let's shift gears for a moment. We talked
Yeah.
about how entropy impacts physics, cosmology, engineering, information theory, even life itself.
Yeah, it's everywhere.
But there's one field we haven't touched on yet.
Which is...
Chemistry.
yes.
Does entropy play a role there as well?
Absolutely. In chemistry, entropy helps us understand why certain reactions happen spontaneously
Okay.
and others don't.
Okay.
It's all about the tendency of systems to move towards states with higher entropy.
Okay. So how does that work in practice?
Imagine a campfire.
Okay.
You've got this pile of neatly stacked wood, a
Right.
state of relatively low entropy.
Okay.
But when you light the fire,
Yeah.
the wood burns, releasing energy as heat and light
Mm-hmm.
and transforming into smoke and ash that disperse into the atmosphere.
So the burning of the wood is actually an increase in entropy.
Exactly. The organized molecules of the wood break down into simpler, more dispersed molecules,
All right.
increasing the overall disorder of the system.
And this happens spontaneously.
Right.
You don't have to force the wood to burn. It just does it on its own once you provide that initial spark.
Right, that's because the products of combustion, the smoke, gases, and ash, have a higher entropy than the original wood.
Okay.
And the universe, as we've learned, favors those higher entropy states.
So in a way, entropy is the driving force behind the campfire. It's what makes the whole process happen.
In essence, yes.
Okay.
And this applies to a wide range of chemical reactions.
Right.
Some reactions are naturally driven towards products with higher entropy,
Okay.
and those reactions will tend to occur spontaneously.
It's amazing to think that this concept we've been exploring, this tendency towards disorder,
Right.
is so fundamental that it even dictates how molecules interact with each other.
It really is. Entropy is everywhere.
Yeah.
And understanding it gives us a deeper appreciation for the interconnectedness of everything in the universe.
Well, you've certainly given me a lot to think about today.
That's the goal.
We've gone from messy rooms and unshuffled decks of cards to the fate of the universe, the secrets of encryption,
It's all connected.
and even the chemistry of campfires.
Yeah.
It's amazing to see how entropy touches so many different aspects of our lives.
It's a fascinating concept.
It really is, but I think my brain needs a moment to catch up with all this new information.
Sure, we can take a break.
We'll be back in a few minutes to wrap up this entropy exploration and see what other mind-blowing insights we can uncover.
Sounds good.
Don't go anywhere. And we're back for the final stretch of our deep dive into entropy. I have to say, this has been one of the most mind-expanding conversations I've ever had.
It's a topic that can really get you thinking.
It really does.
Yeah.
We've gone from the basics of disorder and randomness to exploring how entropy influences everything from time's arrow to the fate of the universe.
It's quite a journey.
The efficiency of our machines, and even the delicate balance of life itself.
It all comes back to entropy in the end.
Absolutely. It's one of those concepts that once you learn about it, you start seeing it everywhere.
It's true. You can't unsee it.
But I'm still grappling with some of the bigger implications. If entropy is always increasing, does that mean the universe is ultimately destined to become this boring, homogeneous soup you described earlier?
Right.
Is there any hope for pockets of order and complexity to persist?
That's a question that has fascinated physicists and philosophers for a long time.
Yeah.
While the overall entropy of the universe is undoubtedly increasing, as dictated by the second law of thermodynamics, that doesn't necessarily mean that everything is fated to end up in a state of uniform blandness.
So there's still room for pockets of order and complexity to arise, even within a universe that's tending towards greater disorder.
Exactly. Think of it like islands of order forming within a vast sea of increasing entropy.
Okay.
These pockets of order can arise when energy flows through a system, allowing for local decreases in entropy, even as the overall entropy of the universe continues to increase.
So it's like how life on Earth has managed to evolve and thrive,
Right.
creating incredible complexity and beauty, even though it's ultimately subject to the laws of thermodynamics.
That's a perfect example.
Yeah.
Life is a testament to the incredible things that can happen when energy flows through a system, creating pockets of order and complexity that seem to defy the overall trend towards disorder.
But even those pockets are temporary, right?
Well, yeah.
Eventually, even stars burn out and life fades away. Does that mean it's all just a futile struggle against the inevitable?
Well, futile might be a bit strong.
Okay.
I think the key takeaway here is that entropy doesn't negate the beauty and complexity that exists in the universe.
Okay.
It simply provides a framework for understanding how those things arise and evolve over time.
So it's less about a fight against entropy and more about appreciating the incredible feats of order and complexity that emerge along the way.
I think that's a great way to put it.
Yeah.
Understanding entropy allows us to marvel at the intricate dance between order and disorder that plays out all around us. From the formation of galaxies to the emergence of life, to the simple act of lighting a candle.
You know, you've managed to take a concept that initially seemed kind of bleak.
Yeah.
This idea of the universe inexorably moving towards disorder and reframe it as something almost awe-inspiring.
It's all about perspective. Entropy is a fundamental law of the universe, but it doesn't dictate a specific outcome. It simply sets the stage for an incredible array of possibilities for pockets of order to arise and create beauty and complexity, even as the overall entropy continues to climb.
I love that seeing entropy as a catalyst for creativity and complexity rather than just a harbinger of ultimate doom.
And remember, it's not just about those grand cosmic events.
Right.
Entropy is at work in our everyday lives, influencing everything from the way we organize our homes, to the way we communicate information, to the way we cook our food.
It's amazing to think that a concept that started with physicists studying heat engines can have such profound implications for how we understand the universe and our place within it.
It really speaks to the power of scientific inquiry and the interconnectedness of everything.
Well, we've covered a lot of ground today, and I have to say I'm leaving this conversation with a newfound appreciation for entropy. It's not just about disorder and randomness. It's about the flow of energy, the emergence of complexity, the arrow of time, and the delicate balance between order and chaos that makes the universe such a fascinating place.
It's been a pleasure exploring this topic with you.
The pleasure was all mine. And for our listeners, if you're still feeling a bit entropy-addled after this deep dive, don't worry, that's perfectly normal. This is a concept that takes some time to wrap your head around. But hopefully, we've sparked your curiosity and given you a new lens through which to view the world. So until next time, keep exploring, keep questioning, and keep diving deep into the wonders of the universe. And maybe just for fun, try tidying up it in defiance of entropy. See you next time.